Thank you very much for this invitation, for this presentation. And I'm delighted to be back. It's my second visit to Hefei. The previous one was 10 years ago. But my next one will be much sooner than 10 years. So I look forward being here. I've been practicing my Chinese, so ni hao. And um, I'm going to be talking about a topic that I think is important to many of us, the topic of fire science and the context of modern ideas like fighting climate change and sustainability and net zero. These are big words that many universities around the world pronounce. So, but my name is Guillermo Rein, and I am from Imperial College in London. So I don't know how many of you have been to London and to visit us. This is an official invitation for all of you to come and see us. We are in London, in central London. So if you go to the museums like Natural History and Science Museum, Victoria and Albert, Hyde Park, then we are literally just there. Very recently, we were very happy that QS rankings put us second in the world next to MIT. We are very comfortable next to MIT. Everybody is very happy to be next to MIT. We are very happy to be there. And we are the leading university in Europe. So whenever you want to see us, please do so. This is how it looks. Our campus is, no, this is, all of this is Imperial College. All of this, my office actually in particular is there. And this is a beautiful street that many of you might have been to London visiting the street. So you just need to turn right and then you will be next to us. So please come and visit us. This is important in particular for this institution, USTC and the State Key Lab, because we do have already signed an agreement of a memorandum of exchange of ideas, of academics, of students. It was signed in 2021, and it is between my department, the Department of Mechanical Engineering, is one of the biggest departments of mechanical engineering in the world in terms of size, with the State Key Lab of Fire Safety. So it's important that we continue working on this and we continue the exchange. And I look forward, many of you in the room and online, to continue this exchange. So a little bit about me. You have already noticed my accent is not very British. So that's because I was born in Spain. So my accent is Spanish. It's very thick, but it's okay. Hopefully in a few minutes you will start to get it. I left Spain. I studied engineering in Spain, mechanical engineering. I left Spain to go to the United States. I studied in California at the University of California, Berkeley, where I started to do fire science. I was working for NASA, taking care of the safety, fire safety of a spacecraft. And then I went to the UK, first in Edinburgh and then at Imperial to become an academic. So now home is the UK, and I want to stay there for the rest of my life until I retire. But I just wanted to know this little triangle, and now today we are here. So a lot of movement in the Northern Hemisphere. As also already mentioned, I'm very proud, tremendously proud, to be the editor-in-chief of Fire Technology. This is one of the leading journals. That we have 4 journals in fire science, and then we have other disciplines that also do fire science. No, but of the ones that only do fire science, this is one of the leading journals. We are the oldest journal. It was created in 1965 and continue publishing. So there is a lot of history. When you go into our online archives, you have access to all the fire science since 1965. So not just the latest papers, but you have also the papers of our founding parents, which is important. We are associated with the NFPA in the United States, the National Fire Protection Association, and the Society of Fire Protection Engineers. So we are their scientific journal. We do science to make sure that it's used, right? And whenever we look, we can look into submissions, we can look into downloads, we can look into impact factor, we can look into the site score. What we are seeing is that the journal is buoyant, it's succeeding, it's going up. So I want to highlight one of these steps. Look what happened here. You know what happened here? And it took off, that I visit Hefei. So my expectation is that after this visit, right, I'll be here. Okay, so when I come back, I hope the journal is up there, right? Thanks to actually USTC, you are really important. I mean, you know this, but I'm just going to tell you. your institution, all of you, are really, really important for fire science in the planet. You are the biggest fire group. You are my favorite partner, actually, in the world. The amount of work that you do is incredible in quality, style, impact, and value. And if this journal were to continue succeeding, it has to include you. So the more of USTC that we have in the journal, the better the journal does, and then you get the impact factor and the and the qualities that you need for PhD theses, graduations, and promotions and projects. So I'm asking officially for an investment of USTC into the journal, and then the journal will give you back what you want, because you are so big that you are almost a quarter of at least a third of the fire science community. So please know that we have 2 associate editors in the journal, and we get papers from USTC, but I know that the best papers of USTC go to other journals. So I want to attract us into this journal. I want this to be home for you. So now we're going into the topic. Obviously, didn't do all these things without the amazing help of my group. Many familiar faces here that I saw yesterday, my Chinese former students. Xinjiang Huan, now a professor, associate professor in Hong Kong Poly. Uchi Hu, he's now in Chengdu. Han Juan, Sengwen Hu, Suan Sehe, Uchan Kui, and we have, I saw them yesterday. They flew from different parts of China, and I saw them yesterday, and it was really nice because I haven't seen them in such a long time. So it was a very nice reunion of my group, and I look forward having more of them here, right? So when I come back in my next visit, there will be a new row with more Chinese students in it, hopefully. So let's start. So we are all involved in science. One of the joys of doing science is this journey of discovery. We discover, together with our teams and our colleagues and our communities, we discover new things. This is what science does. Discover things that were there, we observe them, we do computer models, we do experiments, we develop new theories and new understanding. And it's truly the joy of scientific discovery. Now, obviously, it doesn't come without difficulties. The exhaustion of the trip. Very often we look in the wrong place. Sometimes we think we found something, but we didn't. But at the end, when we look back into our careers, it is a journey of discovery. As an engineer, not just as a scientist, we also believe in creating these wonderful things that engineers do. These things that nature would not do. This is what engineers do, things that otherwise would not exist. And these things bring comfort to society, allow civilization to progress, development, and safety. And the combination of the 2 of them is what we do as professionals. And always, once or twice or 3 times with our careers, we find our own disciplines, no matter which one it is, at Crossroads. Crossroads is that you're having a journey and suddenly you have an option that we didn't expect of changing directions, of changing the way we thought we were going to do things, because things have happened in society, things have happened in our field, things have happened in our lives. So crossroads are something really important to keep an eye on in every issue, things that we do in life. In our field of fire safety, especially coming from combustion science, we are facing some big crossroads. When I started into this field, these crossroads did not exist. So these are very modern and are really important. Not taking these crossroads could have significant consequences to our field. Some of these crossroads are big things like fighting climate change and adapting to climate change, net zero, and the ability of different authorities, governments, and institutions to help us balance the amount of carbon in the atmosphere and to have cities and a world that is sustainable not just for us, but for the next generation. So these big things, when I was a student did not exist, and these things are important. These are crossroads. So we, as fire scientists, need to decide if we take these crossroads or if we just continue without looking for this topic. So I'm suggesting today that we fully look into these crossroads. And I know, for example, that USTC is leader into looking into these crossroads. So the things that I'm going to be mentioned today are things that USTC and the State Key Lab is already doing. This is just related to something that is very important. I don't know if I like it a lot. In psychology, there is a concept of Maslow hierarchy of needs. Maslow was in the 60s. He was actually an engineer. They came out with the realization that this is where we want to be, all of us, every single person in the planet. We want self-realization, self-realization. We want our dreams to come true. We want our happiness to develop. We want our families to be there, right? In order to do that, we have to be recognized, we have to work in society, we have to be safe, and we have to have our psychological needs. This is that we are able to drink and to sleep and to eat. So this is very foundational. If we don't have the foundations, we cannot realize ourselves as individuals, right? And social needs are here. I know this is very important for China. But look what is just below, between us in society and us being able to eat. In between them is safety. If there is no safety, if our communities, our societies, our countries don't feel safe, they cannot self-realize. So this is a very important pyramid, and it shows you how safety science and fire safety is at the core of human development. Without this, there is no point to continue working forward. And in the course of fire safety, we've always been fighting against the problems of fire and toxicity and all the problems that flammable substances, being solids, liquids, or gases, produce. So this is the topic that we are discussing. I'm now from London. No? My family is from London. I live in London. In London, as every other country in the world, we have a big fire that everybody relates to. Every single nation in the world is able to refer to a fire. In London, we teach our kids about what happened in 1666. That was a long time ago, because it was a fire that wiped London. 3/4 of London were gone. It literally almost, they were lost. The whole city was lost. It was very dramatic. It happened in 4 days, and it became a historical event that now is taught. It's in the books, and it's taught to kids. So my kids, for example, because they grew up as Londoners, they were taught the Great Fire of London of 1666. It redid London. So the modern London that we know now is different because of what happened in this fire. But there are many lessons that should not be forgotten. Every country goes back to their fire and their lessons, but these are important things. And for us in London, what happened in 1666, we're there. So then we're talking about combustion science is the understanding of how things burn. Put it into mild context. Now, many of us are fellows of the Combustion Institute, where combustion science happens at the global level. We are talking about safety. We mentioned the importance of safety for self-realization of society. And the intersection between these two worlds, this over here is fire research. That's us, right? How important it is, right? Combustion and safety is a sizable topic. Will always be there, and there are so many things that need to be done. We're going to be busy with it. And then we have the crossroads of society: climate change, net zero, and sustainability. The intersection of these 3 topics is what I want to discuss today. The fact that we are doing combustion for safety in a modern environment. So this thing over here, which is a sizable amount, is us bringing attention to modern topics that society are demanding from us to bring them safety based on the knowledge that we have of fire. So this is what all of us are doing. So the 3 topics that I'm going to be, obviously this could be a whole week of discussions of how fire affects sustainability, but I've decided not to. Next time, hopefully you will invite me for a week of lectures. If not, I'll just talk about 3 topics and quickly discuss things forward. So the first one is going to be wildfires. Why is wildfires into this modern view? Timber and batteries. And as I speak, I know USTC is world leader in the three of them, and it has really important research that is happening in the past years and as we speak on the topic. These three topics, wildfires, timber, and batteries, is just three examples that I chose because I happen to be active on them. But there are many, many more. Maybe we can discuss it during the questions. But there are other aspects, for example, facades, insulating facades, green walls, wind turbines, solar panels, nuclear power plants. Just think of anything new that has arrived as an innovation to society. It always, unfortunately, has a fire hazard associated to it. Sometimes we recognize the fire hazard right away, maybe in wildfires. Sometimes we actually struggle to recognize the fire hazard. So maybe this happened with batteries. Batteries have been with us for 20 years, and it took the battery industry a really long time to recognize publicly that they have a fire problem. So now we know they have a fire problem, but it took a really long time for them to be embracing safety. So we start with wildfires. Now, the context of wildfires that we are happening is wildfires have been happening in the planet for millions of years. We became a species, the human species in the planet, and there was already wildfires burning. And we humans learned wildfires from nature. So we became the first species in the planet that instead of running away from wildfires as every other species of animal does, we became the only species that turned around and started to investigate what is this, right? Probably our ancestors burned their hands and their hairs and everything. And fast forward, now we have power that is arriving to us through the taming of fires and the metallurgical processes, the chemistry, the comfort of heat is a success story. But wildfires continue burning outside our towns, the natural cycle of wildfires. When we look into what has happening with wildfires, for example, we can identify, this is a nice set of data from the United States. It's a very old plot, but it's okay, it still works. It goes down to 1985. It actually captures about 30 years of wildfires. And we could look into the blue. The blue is the number of wildfires that were detected in the United States of America that specific year. I use the US because it's the best database that we have. I wish it was Spain or UK, but no. The best database on wildfires is the Americans because they've been looking into this for longer with all their abilities. So we see that the number of wildfires is insane. We're talking about 100,000, but it actually is not changing. It's just going up and down, up and down. So when we look into the number of wildfires, people say they have always been there, right? We don't have to worry. They've always been there. We will do as we were doing, and we don't have to worry. But that's the number of wildfires. That's saying that a tiny little wildfire that burns half a park is the same as a wildfire that burns 7 towns. That's not fair. No, we have to be able to identify the damage that the wildfire produce. How bad are these fires? So then we can go to the next level. That's the black. Is, for example, a proxy to damage is the size that the fire burned. It's called the burn scar, and it can be measured in kilometers squared, thousands of kilometers squared. And then now what happened? Going up. And actually, since the database has been captured, it actually goes all the way up. So what we see is that wildfires in number might not be increasing or decreasing. The damage they produce is really high and exponentially. We always worry about exponential and exponentially growing. Take into account that the bigger the fire is, the more people they're going to be affecting. If you have a small fire, maybe it's affecting a few houses. If you have an absolutely massive fire, you might be capturing thousands of homes, maybe actually even millions of people capturing in the burn scar. So we as engineers, we are very concerned about this trend. And officially now, even though I know the government of China is very concerned about what is happening with wildfires all around the world. I'm referring to the US database because it's the best one in the world. This is happening all around the world. I am not aware of any sizable country in the world that is not worried about wildfires. I'm not aware. If you're aware, let me know, because every single country that I go, they are worried about what is happening with wildfires in their country. And then obviously when we have something like this, everybody, at least in my world, says, oh, it's climate change. It's climate change. This is caused by climate change. Well, the answer to that is yes, it is climate change, but it's not just climate change, right? So this is what I'm bringing this question to you because it is climate change, but it's not just climate change. It's more things. For example, there are also changes in the land use. For example, virgin forests in the Amazon that has been a jungle untouched by humans for thousands of years. Suddenly now they're being used for harvesting the wood, or for plantations that are being developed in virgin forests. This is also happening in Southeast Asia and Indonesia, where the Indonesian jungle now is being used for plantations of oil plants. So changing the land use typically changes the fire behavior, and it does it always to the worst. It's interesting that when we humans go into a pristine forest, it's not to make it less flammable. We always actually, when we go into the forest, we make it more flammable. So there are changes that are caused of land use. There are also changes in population. People are moving in and out of the forest. We are more familiar with people moving into the forest, as it happens in the United States. People in the US love to live in the forest. But maybe you're not familiar with the fact of what is happening in Europe, which in my home country in Spain, where people are still abandoning rural areas and they're moving into the city. When they do this, they are abandoning agricultural land that has been agricultural for maybe 6,000 years. So suddenly, for the first time in 6,000 years, no one is looking at the land, right? They're abandoning it. And then when we abandon the land, typically it actually starts to become more flammable. So there are changes in population, changes in land use, and climate change. And then we have the more strange of all the changes. Is what is called fire exclusion. This is the most concerning and most difficult to be aware of. And is thanks to the Americans, to North America, we know of the concept of fire exclusion. Fire exclusion is that if we exclude fire from the forest, if we became so good as firefighters that we fight every fire and we stop every single fire, then what we are doing is making sure that the next wildfire is even bigger and bigger and bigger until our capacity to extinguish is overwhelmed and we actually end up with an absolutely immense wildfire that in a way we, by fighting fires, have created. This is uncontroversial scientifically speaking now. When it was put forward the first time in the 70s, government United States thought that scientists were crazy, and they literally said, scientists, what are you talking about? Obviously, you don't know how to collect data. It cannot be the more that we fight, the bigger the fires get. That doesn't make any sense. It's the other way around. The more that we fight, the smaller they get. And now we understand, after 50 years of research, that if we fight the fires, if we exclude fire from the environment where it was created by nature, we start to accumulate the fuel. It doesn't burn, it accumulates. It doesn't burn, it accumulates, and then ends up with so much fuel that when the fire arrives, it becomes a humongous fire that we cannot stop. So the concept of fire exclusion happens in the United States. It might be starting to happen in Europe, in the south of Europe, in the Mediterranean. It might start to be happening in Australia. But it's a lesson for everybody. Hopefully it will never happen in China. That we should not just fight the fires. We need to understand and manage the fire, not just fight them, right? So all these, and it's a mess, right? Because very often, actually, everybody's here. I bet big parts of China are here, big parts of the United States are here, big parts of Europe are here. And when you're here, you don't know why is this happening? Well, it's happening because of this, because of this, because of this, and because of this. So it's very messy. But that's why we, as scientists, study fires in the Arctic. This is the Arctic Circle. That is going to be United States, and that is going to be Europe, and this is Asia, right? So this is the Arctic Circle seen from above. So I'm from Spain. I like warm weather, like Hefei. I don't like the Arctic. It's too cold for me. But as a scientist, I study what happened in the Arctic in wildfires, because in the Arctic, there is no people. In the Arctic, there is no use of the land. In the Arctic, there is no firefighting. So what happens in the Arctic is climate change. That's the Arctic. So when we see changes in wildfires in the Arctic, we are studying climate change and wildfires. And what we see in the Arctic is that unprecedented number of wildfires, increasing in frequency, increasing in size, increasing in damage. And that means when we study the Arctic, everybody can learn about what is happening because it gives us this big bubble of climate change. Some of the topics that we study in the UK in my group is because of the Arctic, because of that reason. Isolates a signal. But the Arctic or not the Arctic, we are looking into protecting people. We are scientists, we are engineers. It is absolutely paramount. I already mentioned this, but it's important to protect people. These are examples of failure of protecting people. In this case, this is a California town. A wildfire arrived from the outside. It crossed the interface between the wild and the urban and started to burn the homes. It became an urban fire caused by a wildfire, and every year, all around the world, even in China, there is about 1 million, at least 1 million people that have to leave their house running because a big wildfire is arriving to their house. It could be an isolated home, it could be a community, it could be, as it happens in London later on, you will see inside the city itself. At least 1 million people have to evacuate. So these communities were evacuated. We're very happy that in this particular photo in California, no one was injured. But when they came back, they had no homes. They had lost their homes. There were no schools for the kids. There were no hospitals for the community. So these fires are wiping out. They're destroying whole communities that have to be rebuilt. And it's very dramatic to lose your neighborhood, your town, your hometown, your city. So this is what we are trying to fight. The amount of damage in California, for example, is really, really high. California right now has to pay in the order of billions every year to reconstruct what the wildfires are happening. This is just California. In reality, it's happening all around the world, but it's quite dramatic, the need for fire safety engineers to help with this. I just want to give you two more examples. One is London, ourselves. 19th of July, 2022, London, I was there. It was a very specific day. There was a heat wave. London is not supposed to be very warm. It's now getting really warm because we are having heat waves. They think it's because of climate change. This was a very specific, very strong heat wave that led to about 400 wildfires. Not fires in buildings, wildfires. These were not cars, buildings, or homes. These were the gardens, the parks, the green spaces, the recreation and the trees in the city, inside the city. This was not in the wilderness fires that arrived to the city. These were fires that happened in the city of London. Right? For example, I was very close to this one over here. I remember I was with the kids at home and I could smell, and I said to the kids, today London smells like the fire lab, my lab. But that's wrong, right? Home should not be smelling like fire lab because the fire lab is where we burn things for research in safe conditions. Having that smell close to home made me feel very unsafe. They were all burning around London to the point that the London Fire Brigade, one of the biggest fire brigades in the world, the 19th of July was the busiest day since the Second World War. So I don't know if you're familiar, but during the Second World War, London was bombed on a daily basis, and it was burning the city on a daily basis. So that day in July, London was at war with wildfires. And this is a lesson that should not be forgotten. Not many cities have felt this. We don't know why London felt this that day. Why did a heat wave do this? It really happened. It was not a dream. It was not a nightmare. It's in the data. And this could be a tale of things to come in the near future. These heat waves that bring what I call now fire waves into cities that are not prepared for this. Another strange phenomena happened the year after, so that was last year, in Hawaii. It's not that far from here. Hawaii, the former capital of Hawaii, Lahaina. It was an ancient town, beautiful in one of the islands. And in the summer, it burned. It was a wildfire outside the city that moved into the city. It completely destroyed the city because it happened at the same time as a hurricane. This, we don't know many cases of this. We don't know many cases of a hurricane driving a wildfire and having a wildfire with hundreds of kilometers per hour of wind. It leads to beyond wildfire, extreme wildfire behavior. It becomes actually something that it cannot be observed with the means that we have. The outcome is an absolute 100% destruction of the city. Even the ships in the harbor of La Jaina, even the boats were burned with all the heat by convection and all the embers that the wildfire was bringing in the direction. So literally, absolutely everything was burned, and many people were talking about one of the highest casualty rates in the United States wildfire history that happened. Lessons need to be learned. It happened under U.S. watch, but everybody can learn from this because we don't want these strange wildfire behaviors to happen. As engineers, we need to protect people, property, and the environment as well. So what can we do? And what is USTC already doing? And what is it that we are doing at London and many other fire groups around the world? Well, we are doing all of the above. We are doing experiments. We are doing experiments in the lab. We are doing experiments in the field. We are doing development of theories of why wildfires behave this way, what is the ignition spread, what is their emissions, how we can suppress all of the above. And then we develop computer models, theoretical models or computer models. This one in particular is just a very famous equation that was developed for Farsight. And we combine all this. We do all the things that are already happening and we put them together, experiments, models, and theory. This is the circle of fire science. We need to do all of the above. Some people just do experiments, fine. Some people just do models, fine. Some people just do theory, fine. But all together is what brings solutions and understanding. It cannot be that one community just with one approach will lead. It has to actually be all of us coming together in a cooperation, in a sisterhood and brotherhood of approaches. And what we are already delivering and what we will continue delivering to the people that are waiting for us, so we provide safety. Well, it's a long story, but I like to tell this story in the concept of the layers of our protection. So in this picture over here, we are seeing already the things that we can do to protect. For example, first, and this goes in order of chronology, we can prevent the fire. We can prevent the bad fires. And remember fire exclusion. If we only prevent, we end up in a worse situation. So we need to avoid ignitions, but we need to promote the good fires. In wildfire, this will happen in the building. In the building, no fire is good. Just avoid. In the forest, we avoid the bad fires. We promote the good fires. Good fires are the fires that have the right intensity and the right frequency. And if they have the wrong intensity and the wrong frequency, they become bad fires. So prevention, very important. I'm not saying prevention in simple terms as don't play with a match, don't bring a lighter here. I'm talking about technical prevention, theoretical prevention, which is a probabilistic way of saying ignition sources have a distribution of power and frequency. Fuels have a distribution of flammability, and you don't want the two of them to intersect. You don't want high ignition power ignition sources to find highly flammable fuels. That's the worst case. So you want to separate the ignition and the flammability of the fuel. If we have failed in prevention, that's a breach of the first layer, then we have more layers to help. It's not the end of it. Okay, there is 6. Just there is a wildfire. It's a bad wildfire. We could not prevent it. First thing that we do is to detect as soon as possible. The earlier our detection system, the more things we can do. Detection per se doesn't do anything. Detection per se is a layer that allows all the other layers to kick in. So we need to detect. We need to know that this is happening. We can use satellites. We can use watchtowers. We can use people in the forest, people that are living in the forest. We can have drones observing this. We can have many different ways of detecting. One thing that we can do, we can suppress. This is the most popular. I mean, you're fire scientists, but this is what people think that's the only thing that we can do. So if you go outside this campus and you are a citizen, they think that the only thing we can do is suppress. The only thing you can do when you have a wildfire is call the firefighters. But we know we can do more. Suppression is really important, but it's just 1 out of 6. And suppression is put down the flames, right? Another thing we can do is compartmentalize. It's a complex word. Is to create compartments, even in the forest, in the sense that one forest, one site, one region is burning. We should not allow the fire to jump from one side to the other. We should compartmentalize either ahead of time, what is called fire breaks, and sometimes highways can act as fireways or rivers and even valleys, or maybe we do the fire breaks in real time, which might take 1 or 2 days. Okay, but compartmentation is very important, and combining the two is fantastic, right? Compartmentalize and suppress. And there are 2 more. Fifth, very dramatic. I already alluded to this. Sometimes we have to evacuate communities because we cannot prevent it, we cannot stop it, we cannot compartmentalize it, but we have seen it. So we need to take people away, evacuate communities. We're talking about by the thousands. This is a topic of research that is very active. And the last one is brace for the incoming wildfire. We have failed stopping this wildfire. Hopefully we have evacuated, but the wildfire is coming. Now we need our buildings, our communities to be resilient and strong and be able to contain the damage. There is going to be damage, but hopefully it will be not too much. Hopefully the community can recover, fix, mend, and come back to life again after the wildfire. And this is in order of chronology. Prevention will be the first damage. In the cases that I told you before, the Lahaina and Hawaii and London, all the layers fail. This is what is called a worst case scenario, breach of all the layers, right? Cases that we don't know about are cases where prevention was not breached. We don't even know. If the fire didn't happen, we don't hear the bad news. It's quiet. Quiet is good, right? Or maybe the fire happened and it was detected and then it's suppressed. These are case studies that we can think of. Second topic, sustainability. Sustainability is a balance between the environment, equity, and economy. Equity being fair not only just with us, but being fair to the next generation, which will inherit whatever we do, for good and for bad. So sustainability is something that engineers have been doing for a very long time, but they didn't know that they were doing it. And now we've been asked to do this explicitly. So for example, one way of doing sustainability is not to only build in steel and concrete. We can build beautiful buildings out of steel and concrete, but we have discovered that sometimes steel and concrete are not as sustainable as we wish them to be. So one of the ways to build cities that are sustainable or buildings that are sustainable is to make them out of wood. We humans have been making homes out of wood for millions of years, right? Our first homes were actually made of wood. They're not in the historical record because wood degrades and it doesn't leave anything. And then we started to build in other materials. But it's not a revolution. We've been building with wood for a long time. Now it's high-rise buildings, skyscrapers, tall buildings made of timber. That is what is unusual. For a very long time, this is an example in Norway. This is a high-rise building made of wood. It's not that the exterior looks wood, it's that the structure, the inside, the load of the building is being carried by wood. And that requires what is called engineered wood, mass timber, in particular CLT, cross-laminated timber, which is humans improving upon the trees, realizing that trees are amazing, but not perfect, because they only carry loads in one direction, whereas the engineer needs the structure elements to carry the loads in 2 directions at least. CLT and mass timber does that. So now it is possible, structurally speaking, to build out of timber. What happened? This is an example of CLT, right? You are combining loads in 2 directions. So this block can carry loads in 2 directions, whereas each of them, which comes from a tree, can only carry load in 1 direction. It's CLT, engineered timber. The problem is that timber is amazing, it's beautiful, we love it, captures the carbon neutral, inexpensive, people like it, right? This is actually wood, it makes us feel comfortable, the view of wood, but it's flammable. All good products known to humanity are flammable. Some of them are very little flammable. Some of them are extremely flammable. But there is a need to understand the flammability of wood products. This is an example of what happens in time if you have a block of wood and you expose it to a fire or to heat. Right? It starts to degrade. You start to have wood that dries, and then it chars by pyrolysis, and then this char might actually oxidize itself by osmoldering and disappear. So at the end of the day, what you end up is you lose timber. So not only is flammable and creating a fire and creating a hazard and having people to evacuate and be away from fire, is that the structure is losing section. And engineers know that if you lose section, you lose the capacity to carry loads. So now the structure is weak and it's a high-rise building. So it is a concern. And that means that high-rise buildings made of timber can be done, but they require the highest and most advanced fire engineering that we can get, because it is really difficult to get it right, because it's more flammable and it actually, the structure is weakened by the fire. How we would do this? Well, we would do all of the above. We would come out with experiments, we will be measuring, and we will coming out with solutions to the structure. These are the multiple steps. We have also computer models, and we have ability to calculate. And at the end, we end up is creating guides based on science that engineers can read. For example, this is a very famous guide in Europe. It's called Eurocode 5, and it's a guide that teaches structural engineers how to design in wood. And the Eurocode 5, which is a book that is revised every many years, has a significant section on fire. And it teaches engineers what they have to do to calculate timber in fire. And that chapter, the fire chapter, keeps getting thicker, because the science that we are creating is being fed to the engineers, and the engineers are learning how to do this better and better and better. And at some point, the safety of their methods would be that we can have not just tall buildings, but very tall buildings, because we will be confident that they can be safe. And we will be able, sorry, we will be able to have experiments combined with models, as we did with wildfires, and we will end up with something as pretty as having the charring rate as a function of time, evolving in time, and being able to have experiments and computer models agree with each other. So it's not just that the experiments are important, it's not just that the models are important. The emphasis here is the circle of the models and the experiments, talking to the engineers and coming out with improved ways of calculating are essential. And we will help in how to prevent fires by understanding the flammability of wood, how to detect fires in a building that is more flammable than normal, how to evacuate. In a building, we know that whenever there is a fire, we evacuate immediately upon detection. So in wildfires, detection was here. In a building, evacuation is something that we do very quickly, as we can see with examples of design over here, right? Compartmentation is really important in a building made of timber, because the compartmentation will, in time, be breached by the charring rate and the loss of section. We would be able to suppress, especially if it's a high-rise building, we might need to suppress, so the fires above in floors top where firefighters cannot reach can be suppressed as well, and that the building does not collapse due to fire, that is able to absorb the damage, and that we could rebuild, mend, or fix the building made of timber upon it having a fire, right? This is a hot topic of research, and I know many people in this group in USTC do timber research, because engineers realize they cannot do this they can do this really well with steel and concrete. They cannot do this as well yet with timber, and they need science, so they need all of us to help them. The last topic, and I know this is the home to one of the best sets of research that exists in the world, battery fires. So this is related to net zero. Net zero is this concept of society that says that they want a balance between the production and the removal of greenhouse gases. It means that if we are burning fossil fuels because of power generation, then we need to be removing carbon from the atmosphere. And this balance calls for electrification, which China is doing really well, by the way. Electrification, because if we consume power from the electricity, we know how much is coming from fossil fuels and how much is not coming from fossil fuels, and we can help in this balance of net zero. And batteries, as a way of storing energy, is a key player to help us in net zero, in the balance between the production and the removal of carbon. These are an example of batteries. So batteries are really, really important. What are the problems? That now we know that batteries have a fire problem. And let's dwell, although there are experts like Professor Wan here on battery fires. So I want to show you just one example and an overview. Battery fires happens with any type of battery, with any size of battery, and unfortunately with any type of battery technology that we had had. These are sectors that had big fire problems at different years, right? For example, this was in 2003, this was in 2011, this is more recent in 2019. And these are the companies that almost go bankrupt. They almost go bankrupt because they could not handle this fire problem. These are really big fire problems. These are not small ones. These were discussed at the level of boardrooms of the corporation of what do we do with this. This is the tip of the iceberg. The problem that is happening with fires is much bigger, and it doesn't fit into the slide. But I want to show you the problem that we have. This is a beautiful electric vehicle car park. Actually, here you can see from the plate, I think it's in China. And this is the CCTV. It's not an experiment. These are actually a real event, right? So some of you might have noticed something was happening here already. So this car, this electric vehicle, you don't know it, but it's already burning. It has already ignited. It has already ignited because maybe there was an abuse condition, maybe there was a defect, maybe there was self-heating. We don't even know because it's a real event. But this battery, as you see, oh, you don't see it? Well, it is burning. What is going to happen is that by the time from the outside we know that it's burning, it's too late. No, if the video goes very slowly at the beginning, you will see how fast it goes. Imagine that we have a smoke detector up here. Now, too late. Too late. So these fires were actually happening very slowly, but they have an exponential growth. By the time we can see them, by the time our smoke detectors can detect them, that's smoke detector, they can detect that. It's too late. It's too late. Not only is fast initiation, that will be, it's not just that they initiate very fast and they challenge our smoke detectors. Our smoke detectors, the height, the sensitivity, the location, they are designed to stop fires from polymers and wood, which they initiate very slowly. They give us plenty of time to be detected. We are not fast enough when we are talking about batteries. The toxicity of the smoke, not all smoke known to humanity is toxic. Polymers worse than wood. Batteries is the next level of toxicity. It is so toxic that we just know that it's very toxic. We can not quantify yet fully how toxic it is, because the elements the compounds that appear in the smoke and the pyrolysis gases and the off gases is a chemistry that we're not used to look into. The fire spreads faster. It develops, batteries have the ability to develop jet fires. So they don't just take the energy that they're releasing and distribute it evenly over the surface that is burning. It actually concentrates them in little gaps, little holes, and it bends and it creates a jet fire that can be up to several times the characteristic length of the battery. So you have a battery like this that is able to have a jet that reaches here, right? All the energy goes into a very specific direction. That is a concern for the battery igniting the next element that is next to it. So it creates a hazard that we are not used to, these jet fires, right? They last for long. Maybe the peak release rate is the same as other fires that we are familiar with, but they last much longer. They can actually last hundreds of times longer than other fires. They are at lower intensity at that point. So we are not used to deal with fires that last for so long. And they are really hard to suppress. Of course, the battery is designed to avoid any external agent to come into contact with the battery, particular water. We don't want batteries to get wet. Therefore, when we try to suppress, the battery is protected by humans, by engineers, not to let the water reach the battery. So because of all these reasons, I am concerned about battery fires. And I know people agree with 1 or 2 or 3, but in reality, I find it difficult that there is no full agreement into the problem that we have. So I call it the triple hazard of batteries. It's not just that batteries are flammable. It's okay. This carpet is flammable and it's very safe. This boot over here is flammable. This computer is flammable. We are used to have flammable elements around us because we rely on fire engineers. Is that also it comes with an ignition source, a source of ignition next to the flammable element. The two of them packed together very nicely, right? And that when it ignites, it is faster, higher toxicity, spread, longer, and harder. So this is what I call the triple hazard of batteries. I am concerned. I'm just very happy that batteries at this point are relatively safe. And I think there is only a fire every several thousands of batteries that are manufactured, even sometimes several millions of batteries that are released. But in this room right now, right, we all have batteries. And in this room, probably it's already about 100 batteries, right? So very concerning to have this phenomena. What is going to be the solution? Well, the solution is to do experiments, to do nice measurements. There is experiments happening here in USTC. These experiments actually, in a paper that we did together with USTC, the experiments were done in USTC. So I'm really happy about this. We develop theories and concepts, and we help engineers to provide the layers of protection. We want to avoid these fires because they are bad. If we fail prevention, we want to detect them as soon as possible. Batteries have they have smart systems embedded. Not all batteries, but many batteries have management systems inside. It means that they are able to detect the fire inside the battery. They don't need to detect it outside the battery. We already saw when we detect the fire outside the battery, it's too late. We need to detect the fire inside the battery. We need to allow people to evacuate very fast, faster than normal, because the gases are very toxic. We need to rely on compartmentation. This is one, for example, one solution that they use in the aircraft industry. They have big batteries inside the airplane, and they just make sure with a steel box that whatever happens to the battery doesn't get to the rest of the airplane. So that's a compartment type of solution. We want to suppress. We don't know yet how to suppress battery fires. We're still learning, hot topic of research. And if we fail in all of the above, we need to make sure that the system, the car park, our home with the batteries, an airplane, a ship, a spacecraft is happening. As I speak, even satellites have batteries, lithium-ion batteries. There is no people, but a satellite is a very valuable device that is sent to orbit with a lot of cost. And it might be orbiting Earth for a decade. We don't want, as engineers, to have a lithium-ion battery in space because they don't need the oxygen of the Earth. The battery has a chemistry that actually has the reactants, all of them, already inside the battery. It can actually happen in space, and it could knock the satellite off. And then actually, not only we lose the investment, we lose the technology and the tool, but we actually create debris all around the trajectory of the satellite. So these are topics that maybe we were not thinking before. Fire hazards in satellites. Well, I've worked for NASA helping fire safety of a spacecraft because there is people inside and they need to breathe oxygen. But now even we remove the oxygen, we remove the humans, and we still have now a new fire problem that happens in satellites. So with this, I'm finishing. Thank you for listening to me. I just want to tell you, the importance of being modern in our fire science and listen to society and realize that climate change, sustainability, and net zero are here and that we need to address them through combustion science and fire research. Just 3 examples. We are very concerned about the increasing frequency of destructive bad wildfires. We are concerned about the safety of tall timber to make sure that it's sustainable. And we are concerned about the triple hazard of batteries. Just as 3 examples of the many different topics that are here. I like to talk about the things that we as engineers can do to address these hazards of any hazards through the concept of the layers and see how each of us might be contributing to the technology of each or all of the layers, and that the better we understand these hazards, the better would be our solutions, and the more we will be contributing to a sustainable and safe world. So with this, I finish. Thank you very much.